Welcome to UV Physics Academy. So here we are discussing the solutions of quantum computation. So this is our next question. Calculate the probability of obtaining result plus 1 for a measurement of V bar dot sigma bar, given that the state before the measurement is 0 and what is the state after the measurement. Okay, so here two things. First, what is our measurement? So our measurement operator is this one, V bar dot sigma, and we need to get the result is a plus 1. Okay, so first let me take the measurement operator. So this is the measurement V bar dot sigma bar. Of course, this can be written as V bar dot sigma bar can be written as V1 sigma 1. Here sigma 1, sigma 2, sigma 3 means Pauli spin matrices sigma x, sigma y, sigma z. V2 sigma 2 plus V3 sigma 3. Okay, fine. And after that, we need to get the measured value as a plus 1. So that means here the lambda equal to plus 1. If lambda equal to plus 1, the corresponding projector, earlier questions we have already discussed, the projectors, two projectors are there. So plus or minus P plus or minus equal to I, identity plus or minus V bar dot sigma by 2. So here we have plus, so that's why identity plus V bar dot sigma whole by 2. So if you are talking about the result minus 1, then you have to take 1 by 2 identity minus V bar dot sigma bar. Cool. Now we got the operator and okay, so fine. If this is the operator, now come to the question. So here two things. One is before the measurement, the state is at 0, and after that, after measurement, so post measurement. So the post measurement state, let us suppose this is a psi final. How much? So this is the initial state, and here what we have measured is this one, p plus 1 or p plus whatever it is. So this is the initial state, and we have done this measurement, and what is the final state? This is the question. Okay, fine. So I hope you remember how to find the final state. Okay, so psi final equal to whatever the operator we are measuring. So this is a p plus operates on 0 by under root. This is the state after the measurement or post measurement. So this is expectation value. So that is a p plus get 0. So first let us find what is this numerator. Okay, so come here, and this is our operator, and I'm going to operate this p plus on ket 0. Okay, so this is nothing but 1 by 2 identity. So we can write this as a v1 sigma x plus v2 sigma y plus v3 sigma z operates on 0. Okay, now if identity operates on 0, you will get 0 only. So that is a ket 0. And here careful, sigma x operates on ket 0, you will get a ket 1 plus sigma y operates on ket 0, you get I ket 1. So that's why I'm writing it as a I v2 ket 1. And sigma z operates on 0, no change. So that's why this is a v3 ket 0. So this is the result state. This is the resultant state after operating this p plus. Okay, fine. Right. So if you want, you can separate this as 1 by 2. So 1 plus v3 ket 0 plus v1 plus iv2 ket 1. Now we would like to find this second next word, denominator. So we have to find the denominator. That is nothing but the expectation value. So p plus. So already we know what is a p plus operates on ket 0, this much. And we have to multiply this entire state with the bra 0. So whenever you multiply it with the bra vector of 0, this term remains, I mean, this term won't be 0, but this term will be 0. So because this is the ket 1 and here it is a bra 0. So finally here we got 1 by 2, 1 plus v3, because this is an inner product of 0, that is the inner product of 0 and 0 equal to 1 only. So but here it will become 0. So this state, this term won't come. Fine. So we got this expectation value. So you can take it and substitute there. So this is our last part. Find the state of the system after the measurement. That is the final state. So psi final equal to, so this numerator, if you observe carefully, this is our numerator. So I request you please take this also. Okay. So wait a minute. Yeah. So this entire term as it is, psi final equal to the numerator 1 over 1 by 2. So this is a 1 plus v3 ket 0 plus v1 plus I v2 ket 1. Okay. So this and whole divided by this one expectation value 1 by 2 into 1 plus v3. So this 1 by 2 1 by 2 gets cancelled. So finally we got the answer. The final state or the state after the measurement, which is nothing but 1 plus v3 at 0 plus v1 plus I v2 at 1 by 1 plus v3. Okay, right. Right. So that's it. So if you have any doubt, so please contact. So this is our next question. Show that any measurement where the measurement operators and POVM elements coincide is a projective measurement. So first, what is meant by POVM? So what is this POVM? So this is nothing but uh, positive operator, positive operator valued measurement or measure elements. So this is the set of elements. Okay. So here this is nothing but it's represented by, let us suppose this is the set of a positive operator valued measurement. That's this can be written as a, let us say, EM. So remember, EM is what? EM is nothing but, for example, if your measurement is A, so EM is nothing but A dagger A. Okay. If your measurement operator is M, so E is nothing but M dagger M. So like that. So here I'm assuming my measurement operator, because the question is about the measurement operator. So I'm assuming, let measurement operator, let us say it is MM, measurement operator. Then what is the corresponding EM now? The EM can be written as MM dagger MM. Fine. Right. So here what they are asking is measurement operators and POVM elements coincide, that means equal. For example, if you take the measurement operator is equivalent to that POEM element, that is nothing but EM. But already we defined EM is nothing but MM dagger into MM. So here we have positive operator, so that's why it will be Hermitian. So MM dagger equal to MM. So by using this property, we can write mm equal to em. So em is nothing but mm dagger into mm. So because of this Hermitian property, we can replace this with the mm. Then it is nothing but mm square. So what is this property? This is nothing but a projector. So because a projector operator, I hope earlier classes you attended. So p psi square equal to p psi. And of course it's a Hermitian also. So these are the properties of projector operator, right? So the next question is again about POVM only, okay? And here they're asking to show this one, where is the measurement operator, okay? So then there exists a unitary operator such that equal to under root EM, where EM is the POVM element, okay? So in this case, that EM is nothing but dagger okay, right? So fine. So as usual, let is the measurement operator. Of course, they have given already. Okay, fine, no problem. So measurement operator. So earlier classes we have already discussed about left polar decomposition. So I'm taking that left polar decomposition. So I request you please attend that earlier problems. Okay, so according to this left polar decomposition, can be written as, this is a unitary, and here we'll be having a j. U is on left side and here it is a j, where j is nothing but under root dagger this is the definition of a left polar decomposition. So by using that property, I hope you understand this one. I mean, sorry, this one. So this is nothing but POVM element. So we can write equal to U under root, in the place of J, I'm writing this dagger So what is dagger Which is nothing but EM. So this is U under root EM. So they have used this suffix M here, right? So that's it. So here this is our next question. So they are asking to represent this in a different basis. They are not same. They are not the same up to a relative phase shift. So here let us discuss about this phase. Here two types of phases exist. One is a global phase, another is a relative phase. So what is the difference between these two? First, let me take a global phase. So here we have global phase shift or global phase, and another one is a relative phase. So what is the difference between these two? So remember, global phase, there is no physical significance. So there is no physical significance for this. The reason is, for example, you have two states, let us say psi 1 and psi 2. So these two are differ by a global phase, let us say phi or gamma, whatever it is. That both the states represent the same system. So that means if any two states differ by a global phase, so represent same system, represents say the same system. That's why there is no significance. Let us take an example for this. Okay, so for example, if I take a psi 1 as 1 over root 2, I'm taking this diagonal base. Okay, so 0 and 1. Now I'm multiplying this entire thing with e raised to I pi, let us say. So this is a 1 over root 2. So ket 0 plus ket 1. Now see, this is the global phase. Okay, oh, sorry, global phase term, and this is the phase. So but both the states represent same system, only phase difference is there. But if you come to this relative phase. Okay, so relative phase, there exists a physical significance. Physical significance. The reason is very simple. So the states which are differ by this relative phase represent two different states. So not the same system, two different systems. Let us say, for example, if I have this psi 1, which is 1 over root 2, this ket 0 plus ket 1, and I am taking this psi 2, 1 over root 2, so ket 0, I'm writing this as e raised to I pi 1. Now see, so both are quite different. I mean, quite different. So here, this is the phase term. Okay. So here the phase is equal to pi, and here also phase pi, and here also phase pi. But this is the relative phase, and this is the global phase. So here we can't say this is psi 1 equal to psi 2. Here psi 1 is not equal to psi 2. So that's the difference. Okay. So finally, of course, the question is about that diagonal basis only. We can write that diagonal base is nothing but 1 over root 2 ket 0 plus ket 1, and this minus a state 1 over root 2. So ket 0 minus a ket 1. So please try to understand the difference between global phase and this relative phase. So the states differ by a relative phase shift, definitely represent two different systems, and here which are differ by a global phase, then both represent the same system, right? Next, here they are asking the average value of the operator x1 z2 for a 2 qubit system. Okay, fine. So I hope you have this idea about this Bell state. This is nothing but a Bell state. So let me explain. So this Bell state, the general form of a Bell state is B, beta x, y, or B, whatever it is, no issue. So which is given by 1 over root 2. Okay. So this is a x and y indices. Okay. So here we have 0 y plus minus 1 raised to x, and this is 1 y bar. So this is our Bell state, general representation of the Bell state. So by changing this indices 0 0, because of 2 qubits, that's why 0 0 0 1 1 0 1 1. Okay, so you will get a beta 0 0, a beta 0 1, a beta 1 0, and a beta 1. So I request you, you please substitute this x and y here and get these 4 states. Okay, right. Now come to this. And here they are asking the expectation value of x1 z2 on this Bell state. Okay, so the given Bell state is nothing but beta 0 0 1 over root 2 0 0 plus 1 1, because if you put x equal to 0 and y equal to 0, so this is 0 0, and here you will get plus 1 only, and this is a 1 a 0 bar, which is nothing but a 1. Okay, complement, just like complement. Fine. So for this state, we have to find the expectation value x1 z2. Okay. So let me write this beta bra vector x1 z2 beta ket vector. Okay. So here I'm writing this bra vector 1 over root 2, 1 over root 2, we can write 1 over root 2 whole square. So this is the bra vector 0 0, bra vector 1 1. And here we have x1. Actually, this is x1 tensor z2. Okay. So again here we have 0 0 plus 1 1. I hope you know the notation of this 2 qubit states. This is nothing but tensor product of 0 0. This is the tensor product of 1 1, like that. So forget about this bra vector. So what is the meaning of this? Observe carefully. So first we have to operate this operator on this. Okay, you can find the matrix and multiply with the matrix also, no issue. So x1 stands for it's operate on first qubit, and this z2 stands for operating on second. And similarly here, this one operates on first, and z2 this one operates on this second qubit. First let us find that. Then it will be, so x operates on 0, you will get 1, okay, 1, and z operates on 0, 0 only. Next, x operates on 1, you will get 0, but z operates on 1, you will get a -1. That's it. So here we have the bra vector, say 0, 0 plus 1, 1, which is the given Bell state. And this is 1 over 2. And if you see this inner product, okay, so there is no common state here because 0, 0, 1, 1 and 1, 0, 0, 1. So all are independent. So that's why if you make this inner product, what you will get? 0. So the inner product of this x1 z2 for that first Bell state equal to 0. So my advice, again take this another 3 Bell states and please practice, okay, and check what you are getting, whether you are getting 0 or not. So please check. So here this is our next question. So this is a nice question, okay. So listen carefully, please. Now here we have two spaces, V and W. So V is the Hilbert space and W is the subspace. So first let me explain the question here. So for example, I have some Hilbert space, let us say V. Okay. Now this will Hilbert space is having a subspace W. So let us suppose another subspace we have. Let us suppose this is the W. So W is the subspace of this Hilbert space. Okay. And so whenever you have defined this as subspace W, and here they are defining an operator U in this subspace W, which is nothing but which transforms W to V. Okay, so that means what? Here we have to define some basis. Let us suppose the basis states. I'm assuming the basis states as a J. So remember, J are the basis states. J set. I mean, this J is nothing but the basis states of W. Fine. And then here they have defined W1 and W2 in W. Okay. So that means what? W1 and W2 are the two states which belongs to this W. I hope you know. So any state in that Hilbert space, a state vector in the Hilbert space can be written as a linear combination of a basis states. So remember this W1 and W2. Listen carefully, slowly, okay, are the linear combination, are the linear combination, linear combination of basis states. Here what are the basis states? J. Remember this J belongs to, this J belongs to only W. Sorry, this J belongs to W. Okay, fine. Next, they have given this definition. This is straightforward. So W1, U dagger, U, W2, which is nothing but they have given this one, W1, W2. So we can write this as W1 identity W2. So that means what? This is a unitary, of course. Okay. So this implies U dagger U, U equal to I, which is unitary. Fine. Very nice. So I hope you understand up to this. Okay. So just I have explained only the problem. So one more time, this is the Hilbert space and W is the subspace of that, and this W contains the state vectors W1, W2. So here I define the basis. Okay. The state vectors are nothing but the linear combinations of basis states. And this is the statement given in the question only. So which indicates U is nothing but a unitary operator. Remember, U is the operator, operates only on the basis. Which basis? This basis. Remember this, please. Okay. Next, what they are asking is, So prove that there exists a unitary operator u prime. So which, I mean, this is the transformation. So now he is considering the whole space. Now we have to consider the whole space, and here we are defining this u prime. So we have to find this u prime. That u prime is the operator in that whole space, not in this w. Okay, this whole Hilbert space. Okay, and he's asking to show that it just extends u. That means something, if you add to that u, you will get that u prime. We have to find that, and after that to derive this. Okay, let us proceed. Then, so here these bases are strictly belongs to only w. So that means what? We need some other basis which belongs to this v only. So that's why I'm taking this basis. Remember, these are the bases, only v belongs to v. Fine. So one more time. So here I'm writing basis. So these bases belongs to only v, but does not belongs to this w. Careful. Right. Fine. So the explanation of the question is over. Now we are going to define this. So now I'm going to define this u prime. So I think the common sense is saying u plus, and here we have these bases which belongs to only v. So that's why just apply completeness rule, and just I'm adding not completeness rule, sorry, I'm adding that outer products summation over I. That means I have taken that outer product of the basis which belongs to v only. So why you have not considered this basis? I have already considered these bases. Where? Here. So if you have a doubt, let me write what is this u. So u is nothing but a unitary operator. We can say eigenvalues lambda. Okay, let us say. Then we can write it as summation over j lambda j and outer product j. Okay, so let us proceed. So finally here we have defined u prime equal to u plus summation over I outer product. So I have considered the basis which are belongs to only v, this one. Okay, so that's it. Now let us prove what he is asking. So I think, yeah, u prime w equal to uw. So now I'm taking u prime and operating on a w, which is nothing but u plus summation over I outer product I operates on w. I told you already what is a w. These are the states, okay, in the w subspace, which are nothing but the linear combination of base states j. So this is nothing but the linear combination of base states. Let us say cj. Every state vector in that Hilbert space can be written as a linear combination of base states. So if you observe carefully, this is nothing but just split it uw plus summation over I, and let us say summation over j. Okay, cj, and this is I, and this is nothing but a j. Remember, this I and j are independent. Okay, so definitely this inner product is equal to 0. I hope you understand. So j belongs to, sorry, so j are the basis only in the, sorry, j are the basis in the w, but I basis I are the basis states only in v. So that's why both are definitely different. So if you take that inner product, it will be equal to 0. So finally here we got u prime w equal to uw. Next, and in the next part he is asking, okay, that's it. And let us check whether it is unitary or not. So how to check whether it is unitary or not? So you just take u prime dagger Okay, otherwise wait, u prime dagger into u prime. So you know what is u prime? U plus a summation over I, outer product I, okay, into, for this dagger, and this is a u plus summation over I outer product. Now just multiply. It's a small multiplication only, no need to get tension. So first let us apply this dagger, u dagger plus summation over I. Of course, this remains the same. Bra will become ket, ket will become bra. Okay, and this is a u plus a summation over I, again outer product. And if you multiply, so first into first, u dagger u. And if I take this u dagger and operates on this, okay, so remember one more time I'm saying this u or u dagger operates only on the basis states. Which basis states? J. So I is not the basis of I are not the basis states of u or u dagger. So that's why what will happen if this operates on this, you will get 0, and similarly this one also 0. Okay, and the next term whatever you have plus second into second, cross terms are 0, summation over I and sorry, right. So this inner product is 1, of course, and finally we got u dagger u plus this summation over I. Okay, so this is something but already I we have. Okay, and we can say this u prime dagger into u prime equal to I. That means this is related to summation over j outer product j, and this is a summation over I outer product I. That means what? So here you consider the whole Hilbert space. So by using the completeness rule, you have this summation over j outer product j plus summation over I outer product I should be equal to identity I. So we can show that this u dagger sorry, u prime is also a unitary operator. So I hope you understand. If you have any doubt, so please contact. Right. So this is our next question, and they are asking to show that psi is not equal to the tensor product. This is nothing but a tensor product of AB, where A and B are single qubit states. Okay. So what is this psi? Don't get tension. This psi is nothing but our Bell state, that is 0 0. Okay. Bell state 0 0. We have already written 1 over root 2 0 0 plus 1 1. Right. Okay. Right. So entanglement, it is related to the entanglement. Let us discuss. Okay, so here I have to define the two states which are A and B, which are single qubit states. A single qubit state can be written as a linear combination of computational basis 0 and 1. So A1 ket 0 plus A2 ket 1. Similarly, ket B equal to let us say B1 0 plus B2 1. So these are the two single qubit states. Fine. Now let us take the tensor product of these two, and we have to show that the tensor product definitely not equal to this. Okay, fine. So the tensor product of AB equal to. So let me take the matrix representation. That's a better. So I can write this as a A1 A2 column matrix, and this is a B1 B2 column matrix. So here we have A1 A2 tensor, and this is a B1 B2. So just take this entire matrix and multiply with each and every element of this matrix. Then it is A1 B1. Take this entire matrix A1 B2, and take this entire matrix and multiply with A2 B1. So A2 B2. That's it. So if you write in the linear combination of two qubit states, okay, then it is nothing but 1 over root 2 whole square. Okay, sorry, yeah, sorry, I'm sorry, not 1 over root 2, nothing. So there is no 1 by root 2, I'm sorry. So if you write this as a linear combination, this is nothing but first coefficient a1 b1 ket 0 0 plus a1 b2 ket 0 1 plus a2 b1 ket 1 0 plus a2 b2 ket 1 1. Right. So finally I got this tensor product. Let me write one more time. A tensor b equal to a1 b1 ket 0 0 plus a1 b2 ket 0 1 plus a2 b1 ket 1 0 plus a2 b2 ket 1 1. Okay. Now let us suppose this is equal to psi. So what will happen if psi equal to the tensor product A and B? Then what is the meaning of that? If this tensor product is equal to psi, then definitely we must have only a 0 0 state and a 1 1 state. So these two states must be 0. So what is the meaning of that? This implies either A1 0, either A1 0, we can say either A1 equal to 0 or, and one more thing here, beat A2. Okay, so either A1 0, then it will be 0, or A2 0, then also it will be 0. Or you can take another one option also, no problem. So either A1 0 or A2 0. If you take this and again substitute back, what happened? This state is also become 0 and this state is also become 0. So that means finally what we are getting, this A tensor B product become 0. So that is a contradiction. So which is nothing but which is a contradiction. So that's why we cannot write this Bell state as a tensor product of two single qubit states. Okay, right. Go to the next question. And here they are asking verify the Bell states form orthonormal basis. Okay, okay, fine. Let us write the general form of a Bell state beta xy 1 over root 2. So this is 0y, okay, plus minus 1 whole raised to x and 1 y bar. So first let me write what are these Bell states. Beta 0 0 1 over root 2 0 0 plus 1 1. Okay, so here I can write this as a matrix form. So later I will write the matrix form. Okay, so first let me write this beta 0 1 1 over root 2. Remember my x is 0 and y is 1. Just take it and substitute, nothing else. So this is 0 1 and here x is 0, that's why plus, and this is 1 0. Next this beta 1 0. Here our x is 1, that's why definitely in the middle you will get minus sign. 1 over root 2. So first state is a 0y, that means 0 0. But here you will get minus because of this. Okay, and 1 1. Next beta 1 1. 1 over root 2. So here again you will get minus sign. So this is sorry 0 1 minus 1 0. That's it. So finally we got this 4 Bell states, but I would like to write these Bell states in the column matrix, that means a matrix representation. So I'm writing the here beta 0 0, beta 0 1, a beta 1 0 and a beta 1 1. So this is nothing but the column matrix, so which is 1 and last one 1, in the middle 2 zeros, and here beta 0 1 here middle two ones and first and last 0, and a beta 1 0, same as the first one but negative sign, and beta 1 1, same as the second one but with the negative sign. Right. So why you have taken this in the matrix form? So they are asking to show that these form bases. So what is the property of bases? Linearly independent states. So now here I am going to show that this set of this one, the set of these Bell states form linearly independent states. So what is the condition for that linearly independent states? I will find the determinant. If the determinant equal to 0, I will say linearly dependent. Determinant is not equal to 0, linearly independent. Okay. So I'm using that technique of finding the determinant. So I will find the determinant of these things. Okay, these states. If I get determinant equal to 0, then I can say linearly dependent, and a determinant is not equal to 0, I can say linearly independent. So a set of linearly independent vectors forms basis, no doubt. Okay. So how to find the determinant? But unfortunately here we have 4 by 4 matrix, no need to worry. So this is the first column 1 0 0 1, next 0 1 1 0, and this is a 1 0 0 minus 1, and this is 0 1 minus 1 0. So for this we have to find the determinant. It's a 4 by 4 determinant. How to find? Remember. So just convert any row or column which contains only one non-zero element. I repeat, just convert any one of the row or column which contains only one non-zero element. So that's why what I'm doing is I'm taking this first row, see, observe carefully, and I'm taking this last row, fourth row. So R1 is converted by simply adding R1 plus R4. Just I'm adding R1 and R4. Okay. So then this implies the first row is changed. So 1 plus 1, 2, and that is 0 only. And the next element again 0, and the next element again 0. And after that, no change, the remaining as it is. And the fourth row also as it is. That's it. Now it is enough to find, if it is enough to expand this determinant form. Okay. So which is nothing but, yeah, I'm taking this 2 into, actually here I forgot to mention 1 over root 2, 1 over root 2, 1 over root 2, something here. So that is also will be there. Anyhow, oh, okay. So please don't forget to write that factor 1 over root 2 whole power 1 by 4, sorry, whole power 4. Right. So here I'm just finding the determinant 2, 2 into, and remove, I mean, forget this row and forget this column. Then we have this 3 by 3 matrix 1 0 1, and this is a 1 0 minus 1, and this is a 0 minus 1 0. Just find the determinant of that matrix. Let us see. I forgot to write this factor, I mean coefficient, but it does not matter. Don't get tension. Okay, just we have to show that whether it is 0 or non-zero. That's it. So 2 into, so if I take this here, what I will get 0 minus 1, and the next 0 only, and the next plus 1, sorry, okay, anyhow, 1, and this is again minus 1. So here we got minus 2 and minus 1 something, but definitely this is not equal to 0. Okay, so no need to bother about this exact value. Just we have to check whether it is equal to 0 or not equal to 0. So we can say that since the determinant is not equal to 0, this set of all these forms, I mean, these are linearly independent vectors. Okay, that's it. Right. So this is our next question. This is also very nice question. And here E is any positive operator acting on Alice qubit, and show that psi, this one, they are asking to check whether this will take same value irrespective of psi, whatever you are taking. So where psi is the any one of the four Bell states. Okay, so that's what we have to do. So that means this third party, that means they can't they don't know what. So this is related to that um, yeah, information, everything. Okay, fine. So let us do mathematics first. Now here is any positive operator, is any positive operator, fine, that means you can say Hermitian operator. So what is this operator? See, any operator in the two dimension space can be written as linear combination of identity and Pauli matrices. That means any operator, any operator. I think in the earlier classes I have discussed it already. If you have not seen those videos, I request you please go back to the other solutions. Okay, so please check. Any operator in 2D Hilbert space, in 2D Hilbert space can be written as, can be written as linear combination of, linear combination of identity, I mean Pauli spin matrices. So how can you write this? Okay, now you can write our operator, any operator. So we have taken this is E. E cap can be written as, let us say, A naught I plus A1 sigma x plus A2 sigma y plus A3 sigma z. So this is my operator in the 2D Hilbert space. Okay, fine. Now the main part of this question is we have to show that this expectation value uh, takes always a same value irrespective of the size. This is what we have to discuss. Okay, fine. Now I have to find this expectation value psi, this operator E, the tensor I. And you know psi is any one of the Bell state. Okay, here psi is any one of the Bell state. Now for this problem, I am taking a Bell state, first Bell state, but I request you please take another also, another one and try beta 0 0 1 over root 2 0 0 plus 1 1, right? Okay, so now just I am finding the expectation value. So this is nothing but 1 over root 2 1 over root 2 1 by 2. This is the bra vector 0 0, bra vector 1 1, and this is E tensor I, and here we have ket 0 0 plus ket 1 1. And remember earlier we have done a similar problem like this. So this one will operate the first bit, and this one operate on the second. Similarly, this operates on the first, and sorry, this operates on the second. Okay, fine. But remember, your E is nothing but A naught I plus A1 sigma x plus A2 sigma y plus A3 sigma z. Okay, so let me write that 1 by 2 bra 0 0 plus bra 1 1. Okay, and this I'm substituting this C because I don't want to get any confusion. Just let me take it and substitute. So this is A naught I plus A1 sigma x plus A2 sigma y plus A3 sigma z tensor I. Okay, so this entire thing is operating on the first qubit. Okay, and this one operates on wait 1 minute, right? So this operator operates on the first qubit and this one operates on the second qubit. And here we have one more thing, that is a ket 0 0 plus a ket 1 1. Right. Now no need to get tension. Okay. So this is a 1 by 2. This one is as it is, bra 0 0 plus bra 1 1. Now observe carefully. So this is a naught I operating on the first and this I operating on the second. I repeat, this I operates on the first and this I operates on the second. Same state. That's why A naught 0 0 plus the same thing. Again this one operate on the first and this one operate on the second. Same you will get, no change. This is the point actually. So which is the same, exactly same as this Bell state. And the rest of the states you will get a different states. Final states are different states. Only the first term, only this first term will give you the same same Bell state whatever you have taken. If you take another Bell state, again you will get the same thing. Okay, whose probability amplitude is A naught here. Okay, so let me proceed. Plus, I'm writing with another color. So here, if you observe carefully A1, this is sigma x operates on first, you got 1, and I operates on 0, 0. Observe carefully, not at all difficult. And sigma x operates on 1, it's a 0, and I operates on 1, it's a 1 only. See, these two are quite different from this initial state. Okay, let us proceed. Plus, and the next A2, similarly, A2, sigma y operates on 0, I0, okay. I can write this I outside, okay. So sigma y operates on 0, okay. So this is 1, I1, 1, and I operates on 0, you'll get 0 only. Next, again sigma y operates on 1, you will get minus I 0 and 1 as it is. And next, similarly, if you take A3, this sigma z operates on 1, sigma z operates on this 0, it's a 0 only, I 0 only, and but sigma z operates on 1, you will get minus, so that's why this is 0 0 minus 1 1. That's it. So please observe, once you find the inner product and these two inner product remains not equal to 0, and the rest of the inner product, this one and this one and this one, definitely equal to 0. So finally we got 1 by 2. So here it is 0 0 plus 1 1, and A naught will be as it is here outside, and this is 0 0 plus 1 1. So which is nothing but A naught by 2 into 2, so which is A naught. So irrespective of that state, whatever you are taking there, Bell state, it does not matter. Always you will get that probability amplitude corresponding to that coefficient of I in this expansion, this one. Always you will get this. Because only that identity, and here also identity, that will only give you the same initial state, simple, and the rest of that sigma x, sigma y, sigma z are changing the initial state to different states. That's why that inner product is equal to 0. Okay, so I hope you understand, and if you have any doubt, so please contact. Thanks for watching, and thank you.